This is going to be a walkthrough of the technical architecture behind the autofocus system that we have developed so far. You have your UI, which in our case is LabVIEW. LabVIEW can live on any computer because the main services all live on one single Linux computer. The Linux computer, which drives three main services. First one being the OCT frame source, which is where the frames are coming from. In our case right now, it's a simulation. In the future, it'll be a live source. This communicates directly with the image processing service. Computer vision lives on there. Once that processing has been completed, a numeric command is sent over to the stage communication server. And that's how we receive latency stats, how we make everything move. All of this lives under the Linux computer, right? And so the key benefits of this architecture is redundancy. If one service isn't behaving right, we don't necessarily have to look through one whole program and wonder what isn't working the way it should. Everything being split into its own service means that we can focus on just that service, since each of these services, they work off of the series of inputs and outputs. As long as these inputs are processed the way they should be and the outputs are what's expected, we know that we're doing something right. It's great for redundancy, great for upgradability as well. More than likely, we'll have to improve the computer vision from the image processing server as we continue to test. So the computer vision works in a series of 4 major steps. The first one is to apply a blur, and you split the pixels into columns like a 2D array. And then you identify the position of the most intense pixel color jump. So as I go down this red line, for example, I'm going down this red line row by row, and I wonder, when am I going from a darker region to this lighter region? We also look for consistency through a series of tests, but the main idea is, do the lighter colored pixels stay lighter as you go down? And so all of this detection is represented as a scoring system. So as each pixel is split up, we score the pixels as a float from 0 to 1, 1 being the most probable surface detection, 0 being probably not a surface, open air, don't worry about it. So imagine this entire 2D data structure where each pixel isn't a color value, it's just a score from 0 to 1. Right off the bat, we go into our first test where we're looking for where is the most aggressive jump from a dark to light colored pixel. It's going to be these regions. And then we check also, does it stay consistent? The answer is yes. You can see these lines are a little thicker. So both conditions are satisfied. And then we apply a series of penalties would differentiate these brighter regions as opposed to these brighter regions. This is the cornea that we're looking for. These are not part of the cornea, or at least not part of what we're trying to detect. Usually, the higher the detected bright spots, the more likely it is a cornea. This scoring system works because for anything lower than what's expected, you can apply penalties that will further lower the score, which is ultimately why this region isn't represented as a detected surface, but this is. This is much higher, so the score is much more favorable. So the path selection favors this trend. Some constraints with computer vision, of course, it's processing time, which the good thing about that is as our hardware scales, the processing time will also become a lot faster, but it means that we need to be mindful of image sizes. How can we declare a window where the scans are going to be the highest quality? Draw a box with the top of the box being the highest detected surface and the bottom of the box being the lowest detected surface. Now that you have this entire box, you can split the region proportionally so that you can set a focal point somewhere in that box where we will later discover is the most optimal point for scans. Lab integration will just require the swap out of the OCT frame source. Everything else can stay the exact same. The main components are down with these functions. You start off by normalizing the columns. So like these regions right here, the dimmer portions, not be ranked as low just because it's dim. So we go through each column, we figure out the highest score that each column has by default, and then we inflate those scores to match a standardized system where 1 is the brightest of that column, 0 is not as bright. This function is that second test that we talked about where we check to see if after a detected bright region, it stays bright That's what this function handles. This function determines what is likely to be a surface. The idea being the first detected bright spot should be the surface, ideally. So anything below that will be ranked lower in terms of our 0 to 1 scoring system. And then this is the entire logic that handles the path selection. So let's go ahead and see the system in action. Here is our live OCT feed. This is just a simulation coming over our network, but treat it as the real deal. I want to focus. My patient is under my scanner right now. So here's what I'm about to do. Status is good, everything looks okay. Let me click on focus and now take a look. 182 micrometers. This was sent over to the stage. As we can see right here, the stage completed the command in 58 milliseconds. It's very good. I can also adjust my focal points as we test. Let's say we discover that 26% is the best. Let's see what happens. There she is, 26% adjusted. Looks pretty good. So